All right, guys, this is Mark Carrion. This is one of the videos that I'm going to give you guys for the winter break assignment, the independent study on Unit 4. Unit 4 covers chemical reactions, and so we're going to see some examples of those as we go along. Here we've got, this is the thermite reaction, which we'll look at a little bit there. That's where we're taking rust and converting it back into pure molten iron. This is a combustion reaction. This is a log that's being burned. Here we've got an alkali metal and water. Here we've got an acid-base reaction. Those aren't real exciting unless you have a color change going on. So we have that image there. Got a single replacement reaction of copper wire in silver nitrate solution. And then we've got precipitation, which we're going to look at as well again here. So a couple of different things, that we're trying to figure out, and that we'll be going over here as we go along. So those are just some things to keep in mind here as we do this. Okay, so let me get rid of these. Wipe the screen clear here. And so we're going to cover topic 4.1 and 4.2 in this section here. And we'll be looking at this. So in 4.1, it's an introduction to reactions. And one of the first things we need to get down and remember from first year chem is the difference between a physical change and a chemical change. And so here it says a physical change is a phase change or a change in properties, but not chemical composition, meaning you're not going to get a new substance. So in this example, we have water as a liquid going to water as a gas, which would be vaporization or boiling, as we commonly call it. Remember that a separation of a mixture and phase changes are examples of a physical change. Okay, so distillation, chromatography, that's separating a mixture. That's due to physical differences between like boiling point or polarity with chromatography. If it's more polar, it goes with the water. If it's not, it doesn't. Distillation is using a difference in boiling points to get things to separate. So those are all examples of physical changes that we have. So let's move on here. So for a chemical change, you want to know that when substances are transformed into new substances with different compositions, we have chemical changes. Okay, and remember your evidences for chemical changes. This goes back to the beginning of your first year of chem, either a year or 2 years ago, but it's very basic stuff, but we got to remember it. And so, some evidences are the production of heat or light. You get a temperature change, you get the formation of a gas, which is bubbling. You get the formation of a solid, which we call a precipitate, or a change in odor or color. And it might be one of those things happening or several of them. There are times when bubbles form and it's not a chemical change, like boiling water. But, in general, if we look at the whole picture of what's changing, you can tell if it's a chemical or a physical change. You can also tell by the equations. In the last slide, we showed you water going from a liquid to a gas. In these examples that I'm giving you here, you can see that we're getting new substances. So we look at this first one. This is a decomposition reaction, and that's when you go from one substance, in this case, 2 water molecules, and it's breaking up into 2 new substances, hydrogen gas and oxygen gas. So we call that decomposition. It's decomposing from one thing into 2. And another example, that would be hydrogen peroxide breaking up into water and oxygen. Okay. Then we have combustion, and this is combustion of a hydrocarbon. Remember, hydrocarbons are CH compounds. They have carbon and hydrogen in them. And when you react it with O2 in a combustion reaction of a hydrocarbon, you always get water and carbon dioxide. It's the amounts of water and carbon dioxide that will change based on the formula of the hydrocarbon. So if you have a different hydrocarbon, you'll get different amounts of water and carbon dioxide, different mole amounts. And remember that the coefficients in a balanced equation tell me how many moles. Okay. In the third example, we have a combination, or also known as a synthesis reaction. It's also a type of combustion because I see oxygen in it. That's up for debate. Chem teachers argue about whether that's considered combustion. but for sure it's combination and synthesis. So here we've got a magnesium strip. It's probably being lit with a Bunsen burner, reacts with the oxygen, and now we're taking two different substances and combining it into one, which is the combination synthesis, naming that we're using. In the fourth example, we have single replacement reactions. That's where a single element kicks out, and in most cases, it's a metal kicking out another metal from a compound. So here, copper and chlorine are together. They're dissolved in water, but they are considered together. The aluminum is kicking the copper out of there. Copper ends up by itself, and we now have aluminum chloride. So when you get two guys replacing each other, we call it a single replacement. Okay. And I think just, in my class in first year chem, we say this is like a single person here. This is a couple and the partner switch. Okay. So we end up with a new single guy and a new couple there. Okay. In a double replacement, it's two compounds. So now we have two compounds. And in this case, this is the positive ion switching places. So we end up with sodium going with the chlorine and hydrogen going with the oxygen. Really, that water could be written as HOH as well, which really shows it here. We have NaOH, now we have HOH, which is commonly written as H2O, and that's a double replacement reaction. Now, that double replacement reaction is also an acid-base reaction. So we'll look at, some of those things. We'll look at precipitation and that kind of stuff as we go along. But those are the different types of reactions. You can see we're getting new substances every time. Okay, so that brings us to topic 4.2, and we have net ionic equations. Now, basically your objective is shown here. You want to be able to write balanced chemical or net ionic equations, okay, for physical changes. You want to be able to identify the products or reactants in a reaction, and you want to be able to represent ions in a given chemical reaction. So basically, you need to know how to write these equations and look at some of the representations, which will come in topic 4.3. So chemical equations. All physical and chemical processes can be represented symbolically by balanced chemical equations. The reason why they have to be balanced is the law of conservation of mass, which states matter cannot be destroyed or created in a chemical reaction or physical change. Okay, so therefore we must have a balanced chemical equation showing that the number of atoms on both sides are the same and the mass on both sides are the same. So it's often called the law of conservation of mass or the law of conservation of matter. Okay, and that is a really great argument to make for a lot of things. So here we have an example of H2 plus O2 yields H2O. And if we have to balance that equation, we end up with something like this. Okay, so it's going to take two of the H2s for every one O2 to give me two H2Os. So when I go to balance the thing, just remember we have H's on one side, O's on one side, and then we also have H's and O's on this side. Okay, so when I count them up, I have two on the left side and I have two H's on the right side, and on the left side, the reactant side, I have two oxygens, but on the right side I only have one. So we have to figure out how to get that thing balanced out. And remember, when you guys are doing that, you can only change the coefficients. I can't throw a 2 down there. That is not the law of conservation of mass. That's a different substance, no longer water. So instead, I have to put the 2 in front. That's going to give me 4 H's now. And that'll give me 2 O's. If I have 4 H's on the right side, I need to get 4 there by putting a 2 there. And I end up with 4 H's and 2 O's. When that score, remember that score is tied, this thing is balanced. You can see it here. Okay, so we have our balanced equation. So that's just balancing a normal chemical equation. Just want to review that with you guys before we move on. Okay, So let's look at the different types of equations you'll run into when you guys are doing net ionics. So the first is the formula equation, and this is what you guys are most used to. Okay, we have everything in the equation shown. This is a typical formula equation. This one's already balanced the way that it's written, and it's ready to go. Now, if I take and split it up, and you'll notice on this one, this is precipitation. And I know it's precipitation because I have a solid forming. Okay, the rest of the guys are AQ, which means aqueous, which is dissolved in water. So I am getting, definitely a precipitate out of this. It tells me that. The next type of equation is the complete ionic. And this is where I separate anything that's aqueous into its ions. So if you look at what I've done here, I took the sodium chloride that's shown here, and I split it up into the two ions, throwing a plus in between. Okay, the silver and the nitrate break up into ions, and again, I know that because it says aqueous, so I break that up into ions. Sodium and nitrate break up into ions, so I write them out. The only thing I don't split is the precipitate because it doesn't break up in the solution. It doesn't dissolve. It stays as a solid, usually floats to the bottom because it's more dense, and then we can separate it out by filtering it. Okay, so that gets to stay. That's known as the complete ionic equation. Okay, a very similar equation is the net ionic, and the net ionic gets rid of all the spectators. Okay, now in this reaction, anything that's not making the precipitate is considered a spectator. So if I get rid of the spectators, I'm getting rid of sodium and nitrate. And I did show you guys this in class, but I want to review this. So once we get rid of the spectators, we have what's known as the net ionic equation. You can see that here. Whoops. Go back here. I'm recording this too. Dang it. All right. So here we have the net ionic equation that's going to show up here at the bottom, and it got rid of all the spectators. So the net ionic equation cuts right to the chase, what's making that precipitate. And if it's silver and chloride making the precipitate, that's all I want in the equation. Okay. So the net ionic equation gets down to business and says, this is what's making this precipitate. The spectators, that's great, but they're not part of the reaction. They're just sitting on the sidelines. Okay. So the net ionic equation ditches the spectators. Okay. So let's look at some examples. Okay. So on this practice, it says the formula equation for the reaction of lead-2 nitrate with sodium chloride is shown below. Okay. It also gives you the reminder, and I mentioned this in class, but just remember that all alkali metals, that's group 1A, potassium, sodium, lithium, those guys, ammonium, NH4+, and nitrate, which is NO3-, will always be spectators in a precipitation reaction. What we mean by this is they always dissolve in water, so they'll never be part of the precipitate. Okay. And it says write the net ionic equation for this reaction. So I go right to the equation. I find my precipitate. It looks like it's made of lead and chloride, I should say. So the sodium or the nitrate's going to be gone, and the sodium's going to be gone when this is all done. Okay. Now you'll notice there's a 2 in front of the sodium chloride to get this balanced. Okay. So that means I'm going to need 2 chloride ions. So after I get rid of the nitrate, I now have a lead ion. Okay. If you know that nitrate is a -1 and there's 2 of them, then the lead must be a +2. It also tells me it's a +2 because remember that 2 in lead-2 nitrate means it has a +2 charge or a 2 positive charge either way. So that's going to be my lead. So lead 2+, and that's dissolved in water when it's a reactant. It's dissolved in water there. I take this, I put in the 2 chlorides. That's also dissolved in water, but when they get together as a product, we have lead chloride as a solid, lead-2 chloride, I should say. And that's our precipitate. So that would be the balanced equation. It has to be balanced in charge, and it has to be balanced in numbers of atoms, or in this case, ions. The balance of charge is shown here. We have one lead with a 2+ charge. And we have 2 chlorides with a -1 charge, which is 2 negative. That adds up to 0. All compounds like lead chloride are neutral. They have a 0 charge. Okay. So when you add up the charges on the left, they should add up to 0 on the right. Okay, in that case. And so that's a net ionic equation for lead 2 chloride. I'm going to show it on the next slide too, just so you can see a better look at it here without my handwriting. And remember, note that we left out the sodium and the nitrate because they're always spectators in precipitation reactions. So we have lead 2 plus, lead 2 plus 2 chlorides gives me lead 2 chloride PbCl2, and that's going to be labeled as a solid. You want to be careful on the AP test and the test for this. You want to make sure to label things correctly. If they ask you to write the net ionic equation, you want to let them know what the solid is and what's dissolved in water. Okay, those guys are dissolved in water at first until they make contact with each other, and then they form that precipitate. Let's look at one more example here. Here we have write the net ionic equation for the reaction of aluminum with a solution of copper 2 chloride shown below. Consider the chloride ion to be a spectator. Now, this is a single replacement reaction. It's also known as something called a redox reaction, which we're going to get into in this unit, but we want you to start writing net ionics first, so when we get there, it's not a big surprise. So let's get rid of the chloride in this, okay, first. And I'm going to use a darker color here. So we want to get rid of the chloride. It says it's a spectator. Okay. Remember that this aluminum is aluminum atoms. It has a charge of 0. Okay, atoms don't have a charge, but this copper is an ion. And so in copper 2 chloride, if I just look at that for a second, remember that chloride is always a -1. This is copper 2, which means that's a +2. Or you can just figure it out. You have 2 chlorides, they're -1. There's only 1 copper, so it should be a +2. So we have 2Al, that doesn't change, as a solid, plus 3 coppers with a 2+, and that's whenever it's ions, it's dissolved in water. Okay. Whenever it's atoms, it's not. Okay, in this case, just think of putting aluminum in water. It doesn't dissolve in water. Okay, it's got to be in its ionic form to dissolve in water. So that'll be the left side, and then on the right side we have 3 moles of copper atoms, I should say. So that's going to be written as solid. Again, that has no charge; it's 0. Plus 2 aluminum ions. Now, aluminum, if you look at AlCl3. Chloride always has a -1 charge. The aluminum is a +3 if you look on the periodic table and that pattern. So that'll be 2 aluminum 3+ dissolved in water. Okay, so that would be my net ionic equation for this single replacement reaction. Okay, so net ionic equations can vary. Like for some acid-base reactions, the net ionic equation is really simple. We'll get into this when we get into acids and bases, but the net ionic equation for a strong acid, strong base reaction is just H plus OH gives me H2O, and that's for all strong acid, strong base reactions. So that kind of stuff we'll get into, and you guys will see as we go along, but this is just how to get them cleaned up into just the net ionic equation, okay? So they'll either tell you what the spectators are, or you'll be able to figure them out by the type of reaction as we go through this stuff, but that's what we're looking at, okay?